So the activity that we're trying to develop is just a series of games that you can play using cards and dice, just to teach some concepts related to quantum mechanics. And I tried to come up with an interesting title, so I label it Entangled and Shuffled. Let me know if you think that's better. As I was trying to say, the main question we're trying to answer is what makes quantum particles and systems be different from normal objects, and how can we use them for uh, the field of quantum information science is very multidisciplinary. It sits right at the intersection of science, technology, and engineering. And the main question that we're trying to answer is how can we harness these properties of quantum systems for some technological applications, like making quantum computers or encryption methods more safe, or even sensors that enhance. Right? So during the last century, we saw that there was a lot of technology developed, like lasers, transistors, atomic clocks. And so right now we're living in this time where there's a lot of information flowing all over the place. Now, all that information is stored as zeros and ones inside the computer. And all of that information can be really complicated, but it's really not like the constituent parts are complicated, right? It's just that there are so many of them. So this is a picture of how a supercomputer looked uh, uh, 50 years ago, and now we still have rooms filled with computers, right? So then the main problem is that the resources that we need to use for this keep scaling geometrically. So it's going to be hard to just keep growing like this forever. So quantum technologies offer a potential solution for this, right? But then the main question is, but how do they do that in general? So I would like to introduce like three ingredients that quantum technologies usually have: superposition, entanglement, and interference. So this game in particular, it's more related to superposition and entanglement. Uh, so as you know, I'm thinking this is how the teachers can introduce it. Normal bits are either 0 or 1, so we can think of them as on or off, or maybe with coins, of course, like heads or tails. But now, when you're thinking about the quantum bit, right, then if they are superposed, then we cannot say that they are either 0 or 1 entirely. So maybe one analogy that I like using and the teachers can use is think about a coin, but that is spinning, right? So then you cannot really say if it's heads or tail. It's just a little bit too complicated for that. And say, thinking about 2 bits, so we can have 4 possible states, but then if you have 2 qubits, then in principle, they can be in a superposition of all of these states. And the main key idea to share is that this is somewhat similar to parallel computation, right? So, but then instead of using a stack of CPUs, the parallel processing is kind of a built-in feature of these qubits. So usually, students don't learn about quantum science until they are in an advanced undergraduate class, or maybe even until they get to graduate school. But I think that some of the foundational concepts like probabilities and correlations are things that students can familiarize themselves even from high school, for example. And if we highlight these ideas using regular objects like playing cards and dice, then we can get them introduced to these ideas in a way that is more relatable for them. So these objects are well known, they're easily accessible, they're usually cheap. And the main thing is I want them to think that these ideas are not too hard, that they can be relatable. So I'm thinking first they can start really with just more like a tactile experience in which maybe the teacher hands in some cards or dice, and then they start asking them some questions just to motivate the idea of probability. So this is an idea that is very much related to qubits, because if they are superposed, then they don't have a definite state, and their outcomes come out with some probabilities of being either this or that. So then they can suggest this idea, say, maybe if I roll a dice, what's the chance that I will get a prime number coming out? Or if I am taking cards out of a shuffle deck, what's the chance that I'll get a card that has a letter? So this is just to introduce the concept of probabilities. So I'm thinking this is just something that they can do with the students first, and just that they get used to these objects first. And now another concept that we use in quantum science is the idea of correlation. So in that the results of the different measurements and outcomes can be related to one another. So then for this, we can use these playing cards and maybe prepare some decks. The teachers can prepare them either shuffled or arranged in some very specific pattern, like maybe alternating black and red. And then we introduce this idea of a correlation index, meaning that if we get a pair of cards and the colors match, say if it's red, red, or black, black, then we associate this with a +1. And then if they have the opposite color, then we associate it with a -1. And first, the students can just play with these decks of cards and try to see what kind of patterns they see in the correlations. For example, if you play with a shuffle deck, then you shouldn't see any pattern. This can be an analogy for an uncorrelated system, but if you rearrange it in a very particular way, then that's a correlated system. And now, for the main game that I want them to play, I prepare this board game on which you have to draw 4 cards. So then you have to split the students into pairs, and each one gets 2 cards. And then you start thinking about what kind of correlations I can get between the different cards. So then, say for each pair, then you start thinking, did I get the same color or did I get the opposite color? So you assign +1 or -1 for this correlation. And then this is almost like a game. You put them together in this pattern, like plus, plus, minus, plus, and then just see what you get. And then I think to make it a little bit more clear, I'm just going to switch to a live demo so that we can try it out. This is something I'm thinking the students can do it with actual cards, but this is just a virtual game. So say we draw 4 cards. So say for the first pair, they are both black. So then we assign a +1, right? And so we need to keep looking for different pairs. So for the first one and the fourth one, they have the opposite color, so we give it a -1. And then for these two, this is also -1. Okay, so then you can calculate all the correlations, and then you put them together in this pattern. So it's this one plus this one minus the third one plus the fourth. So in this case, we got a value of 2. And then the idea is that the students can keep trying this around a couple of times. And then the main thing is that if you keep playing this game, it seems like you always get a value of 2. So then the challenge for the students, and this is kind of fun, you can ask them, is there any way on which you could get a value that is larger than 2 in this case? And you can keep playing with the students. I think after a couple times, they should like know that actually you cannot get a value that is more than 2. I mean in absolute value, right? You can get a -2, but then the magnitude never increases. And then I'm going to go back to my presentation. In quantum mechanics, this is called a Bell inequality. An inequality tells you bound, right? So for these correlations, which are noted by this S value, then it's always 2 or less, it seems. And then it seems like it's impossible to get something larger than 2. And this is kind of fun because it's a challenge for the students. But then the thing that you can introduce is that if you do this experiment with quantum particles, and this is really what the people that got the Nobel Prize in 2022 did, but instead of using quarks, they were using photons that were entangled. And instead of looking at black or red, they were looking at whether these photons are vibrating horizontally or vertically, but they are checking whether they are the same or the opposite and calculating all of these correlations. And they got an S value that is larger than 2 if you use quantum particles. So then the main question is how is this possible, right? What is different? And guess the main discussion to have with the students is that when you're just playing with the cards, even if when they are facing down, they definitely either black or red, right? So then you can, once you draw 3 out of 4, then you already know what's the outcome of the last correlation. But once you're playing with actual quantum particles, or maybe we can think how what would be the equivalent of a quantum card, right? It would have to be a card that is kind of constantly fluctuating between black or red. So I have this video, like it would have to be something that you cannot really define the color as it is, right? So then with these extra possibilities, that's why you can get a correlation that is larger than 2. So the main takeaway is that if you use like a quantum particle, which we know it's a little bit more complicated, then it opens up a way for us to surpass the limits that maybe classical computers can have, or classical objects. And I think it's nice just to see this with actual cards, and then it's a game that they can play. So then this is really the lesson that I think they can try on their classroom. And I have tried it with students, and they usually like it because it's like a game that they can try. And sometimes they think that they can get more than 2, and then they explore the math a little bit, and then it really, like they it motivates themselves to no, it has to be 2 or less, but then they try with the quantum particles in my lab, and then they surpass it. So then why is it like that? And it starts. I think it motivates a lot of really nice discussion.